What is an operating system? Hello and welcome to this video. I am Karnesh Johri and this video is an introduction to operating systems. The operating system is the most important part of a computer. It defines what we can do with a computer, how will be its performance, and how will be our user experience while using it. It is a layer of software that sits right on top of hardware and it controls and manages the hardware. Most important, it provides abstraction of hardware resources so that we can easily use the computer. How does it do that? Let's look at it in a little more detail. If we look at a computer, there is a CPU unit comprising of processor, then there is main memory, the RAM, and there is secondary storage comprising of hard disk or the solid state device SSD. And then there are I/O devices like the video display unit, keyboard, printer, etc. We are taking a top-down view, so let's club it all under hardware. Then there is the operating system kernel. Conceptually, this is a layer of software that encompasses the hardware. Once we have this layer of kernel running on hardware, we can kind of forget about the hardware and it appears that there's a virtual machine running the kernel. So, what is this kernel? Is the subject matter of all the study of operating systems. Then there's a layer of software comprising of system programs like libraries, compilers, etc. And quite often, the kernel and these system programs are referred to as the operating system. Like you say, I purchased a laptop with Linux operating system, you actually mean the Linux kernel and the system programs like compilers, etc., which incidentally is the GNU or GNU software, and technically the whole operating system is GNU Linux operating system. So when we say operating system, the meaning depends on the context. And while studying the subject of operating system, the term operating system generally means the kernel. Then there are higher layer software like shell, servers like the HTTP server, editors, word processor, spreadsheet, statistical packages, etc. This is conceptually a top-down view of a computer, and notice the software layers encompassing the layer underneath. We must note that the kernel is the only true layer encompassing the hardware. The boundary between other layers is a bit fuzzy. For example, the HTTP server can directly use the kernel facilities and not bother about the system libraries. Now, getting back to the kernel and how it helps. Suppose there was no kernel and we have to use the hardware directly. Programming would be very difficult. For example, a simple program doing I/O, the I/O device would have to be programmed and it would take a long time to write a simple program doing I/O. Also, running the program would be difficult. One would have to load the program manually into the memory and run it. Only one program can run at a time, and running a simple program would take minutes, if not hours. But all this is not necessary, and writing programs and executing them becomes much easier with the kernel. How does the kernel make it easier to write and execute programs? The answer is that the operating system kernel provides abstraction of hardware resources. It is much easier to use these abstractions and get the work done on a computer rather than use the hardware directly. The kernel provides an application programming interface or API to use these abstractions. The functions of the API are known as system calls. What are these abstractions of hardware resources? Let's look at them in little detail. The job of a computer is to run programs. In fact, that's the only job. Run programs fast, one after other. Run multiple programs concurrently. The operating system provides an abstraction called process which helps in running programs. A process runs a program at a time. The sequence is like this: create a process, The created process reads a program and then runs it. If you want, you can make that process run another program. The operating system provides a system called fork to create a new process. Then there are exec family of calls, and you can run one of the exec calls to make a process execute a program. So there are many processes running in a computer system at any time. The operating system provides inter-process communication, that is, mechanisms by which processes can exchange data. Also, the operating system provides system calls for synchronization of processes. A process executes a program which contains multiple functions. So, a process is executing a function at a time. If you want a process to execute multiple functions concurrently, then the operating system provides threads. A thread executes a function. The operating system provides calls for creation of thread, synchronization of thread, termination of threads, etc. Operating systems provide virtual memory, which plays a significant part in making it possible to provide multi-programming in computers. At any time, many processes are running concurrently. If we look at the physical main memory, parts of many processes are resident at any time. Since there are many processes in the memory, there has to be some way that a process only accesses its part of the memory and does not access the regions of other processes. Also, it is not known at the time of writing a program the location where it would be loaded in physical memory. So, absolute physical memory addresses cannot be used in the program. Thirdly, physical memory is scarce, more so when it is to be shared by many processes. So, it is necessary to augment the physical main memory with secondary storage to meet the memory requirements of multiple processes. Virtual memory abstraction provides a solution to all these problems. Programs need not worry about the physical addresses. Virtual address space is a large memory area that can be used for addressing by a program. Each process gets a private virtual address space. A process only sees its virtual address space and not the actual physical memory addresses. The virtual address space is divided into small units of about 4 kilobytes each called pages. Some of the pages of a process are in physical memory at any time. The rest are kept on the secondary storage. The mapping of virtual address to physical address is done at runtime by the memory management unit. If a program needs to access memory location which is in a page that is not in physical memory, a page fault is generated and the relevant page is moved from the secondary storage to the primary storage by the operating system and the instruction is executed. So we can say virtual memory is an important abstraction provided by the operating system and it makes a significant contribution in making multiprogramming feasible in computers. Concurrency is the hallmark of operating systems. Operating systems provide concurrency. You can do multiple things at the same time. You can run multiple programs in the background and another program in the foreground. It all works without a hitch. Operating systems provide for multiple concurrent processes. If a real life situation has multiple concurrent activities, you can model it as a multiple process system. Operating systems provide mechanisms for inter-process communication in the form of pipes, FIFOs, message queues, and shared memory. The operating systems also provide semaphores for synchronization of processes. By default, each process has a single thread of execution, which is the main thread. Using a library like pthreads, you can have multiple threads of execution. These threads share the global data of the underlying process. So all the global variables in the scope are available to the relevant threads. This causes problem of over availability. Suppose the thread reads a value which is being modified by another thread. To prevent such problems, the operating systems provide mutex object. Mutex is the short for mutual exclusion, and using it, a thread can access a critical section of a code and or data exclusively. Operating systems also provide condition variables which help a thread wait for certain conditions becoming true. Computers deal with data. Data is input, processed, stored, and output. Computers need to store data. The storage must be permanent and reliable. The data stored must be easily accessible, not just to the program that stored it, but it should also be easily accessible to all programs that wish to access it and have permission to do so. For all this, operating systems provide an abstraction called file. Files store data. The files are organized in a file system. There are three kinds of files. Simple data file. This is simply a sequence of bytes. There might be a structure in those bytes, but that is the business of programs that process it. From the operating system point of view, a simple file is just a sequence of bytes. Then there are special files, which are devices, named pipes or FIFOs, sockets, etc. Then there are directories or folders which contain files. Directories can contain all three kinds of files. That is, a directory can contain simple files, special files, and other directories. A directory provides a mapping of a file name to the file itself. So, using a directory, we can reach a file contained in it. Directory imposes a tree structure on files in the system. The tree structure of files is the file system. Here we can see the file system on a Unix-like system, that is Linux. The top directory, the root, is denoted by /. The root contains directories like bin, boot, dev, etc, home, lib, etc. The home directory contains the directories of individual users. So the home directory of user1 is /home/user1, and all directories can contain simple files, special files, and other directories. Computers need to interact with the external world. They take inputs and produce outputs. To do this, computers are connected to a host of input and output devices. The I/O devices are complex and they are categorized like devices connected to serial advanced technology attachment, the SATA, universal serial bus, the USB, etc. A computer has controllers for these group of devices and the devices are connected to the computer via controllers. The controllers are quite different from one another and are much involved. The operating system has a software called device driver for each controller. So when a program makes a system call like read, write, print, etc., the control comes to the operating system kernel and the relevant device driver gets into operation for the I/O. Similarly, operating systems provide an abstraction called socket for network communication. Processes can communicate with other remote processes over the socket interface using a protocol like User Datagram Protocol (UDP) or Transmission Control Protocol (TCP), which are also a part of the operating system. Till now, we have viewed the operating system as a layer of software over the hardware. This gives a virtual machine running the operating system and is essentially a top-down view. There's a bottom-up view, that is, the operating system is a resource manager. A computer has hardware resources, that is, processors, main memory, secondary storage, I/O devices, and the operating system manages these resources. The operating system has to manage the resources optimally, meeting certain objectives. The objectives may be that the response time should be less for users, say the response time should be less than 1 second, throughput should be maximized, certain number of transactions per minute must happen, there should be no starvation of resources. Since our attention is about providing good response time, it should not happen certain processor based jobs don't progress at all. There should be a good network speed. Say the network speed should be more than 10 gigabits per second, the operating system should use algorithms and techniques so that these objectives are met to the extent possible. The resources are scarce, so the operating system implements time multiplexing of resources. For example, there might be a single processor and about 150 processes, out of which, say, 10 are ready to run. So these 10 processes form a ready queue, and the kernel provides the processor to the process at the head of the queue. How is the queue ordered? It might be first come, first served. The process at the head of the queue gets the processor and it runs for the time slice or less if it voluntarily relinquishes the CPU. Then, if it is still ready to run, it goes to the end of the queue. This way, the kernel time multiplexes the processor between ready to run processes. Instead of time multiplexing, some resources might be space multiplex. That is, a part of resource is given to each process. An example of this is the implementation of virtual memory. A part of the main memory is given to each process, and some of the pages of each process's address space are kept in the main memory and the rest are on the secondary storage. The process is only aware of its virtual address space, and the translation of virtual address to physical address and loading of pages from secondary storage to main memory when necessary is handled by the memory management unit and the operating system. Similarly, secondary storage is a resource and a small part of it is given to each user to manage her files. The operating system keeps track of location of files, it manages the free space, and it knows where to write data when a process wants to do a write operation. We have seen that an operating system provides abstraction of hardware resources so that we can easily use the computer. Also, an operating system is a resource manager managing the hardware. You can find all these details at SoftPrayog. You can scan the QR code and reach the web page. Also, the link is given below in the description. Please subscribe to SoftPrayog, click on the bell icon and enable notifications. Thanks very much for watching. Take care and stay safe.